everyone, we're the Anheuser-Busch product recycle team. My name is Amanda Morlang.
Hi, I'm Alex. I will be reading our project abstract. This design project aims to increase the efficiency and sustainability of ethanol distillation at Anheuser-Busch from waste beer. Currently, they operate with a 4.5% ethanol waste stream, presenting challenges of high energy consumption and associated costs for the company. The findings focus on increasing ethanol concentration to 15% through a pre-distillation process to minimize waste and improve overall efficiency. The solutions explored include freeze distillation, vacuum distillation, gas stripping, and a potential combination. These solutions intend to reduce energy consumption, waste, and operational cost. The findings suggest promising outcomes for both freeze and vacuum distillation. However, gas stripping presented less promising results, which indicated safety hazards and sustainability concerns. Further research and implementation by the Anheuser-Busch team leads to significant improvements in efficiency, operational costs, and environmental impact for Anheuser-Busch.
A little bit of background on our project. We're working with Anheuser-Busch. The scale of this process is very large. Their production scale is 10 million barrels of beer a year, which 1 barrel of beer is equal to 330 cans. So as you can imagine, this means the distillation feed to our process is very large. There's actually two 80,000 gallon distillation tanks, which we show the scale to a person. The ethanol is also a very important part of our process. It's a byproduct of beer fermentation, and it can be sold, but it must be purified first. The goal of this project is to make the distillation process more energy efficient to save Anheuser-Busch money on their product waste recycling. This will make it more economically feasible. The diagram above shows the different phases that the current process goes through, starting with the waste beer feed that moves into a single distillation column through a molecular sieve and is sold to a fuel company as a fuel additive. There are 4 objectives for our project. The first one is to increase the ethanol concentration entering this distillation process from 4.5% to 15% ethanol. The second is to research and study pre-distillation processes to design a unit that fits seamlessly into the current process at Anheuser-Busch. The third is to model and simulate the 2 best pre-distillation methods. The fourth is to determine the best pre-distillation method using a techno-economic analysis.
Hello, my name is Denzel Hampton, and these are the 3 pre-distillation methods that we explored to possibly reach the objectives of our project. We looked at freeze distillation, vacuum distillation, and gas stripping. But very early on into our investigation, we found that gas stripping wasn't a viable option due to safety and sustainability concerns. So we went forward with the other 2. Freeze distillation is essentially just freezing the waste beer mixture until just the water freezes out because ethanol doesn't freeze, and we'll have a higher ethanol concentration of a liquid. And in the vacuum distillation, we essentially would be running the waste beer through a distillation column at a reduced pressure, therefore helping reduce energy consumption. All 3 of these options had the possibility of utilizing existing processes, materials, and equipment already in place at the Anheuser-Busch facility, therefore helping increase their sustainability. Now for the market and competitive analysis, the brewing industry as a whole is vastly saturated. It ranges from microbreweries to the big players like Anheuser-Busch. Due to the number of byproducts in the brewing process, most of the innovations in the industry is with the repurposing of those products, and that's where our project comes into play. We are essentially trying to improve the efficiency of their waste beer recovery process, which would then in turn and help them reach their sustainability goals and help them maybe with profits later down the line. Our scheduling budget for the semester, it looks like this. We started off in the research part of our process where we had to learn more about the current process at Anheuser-Busch and investigate different separation techniques that could possibly be a solution to our process. We then moved on to the data acquisition and modeling once we locked down our ideas. We built models in Aspen for the current process, freeze distillation and vacuum distillation. And once those models were built, we started doing optimization calculations. We are now in the analysis and presentation part of our project where we are taking the energy values from the model and testing their feasibility, as well as seeing the techno-economic analysis and if this even makes sense to move forward with. At the end of the semester, we will present our findings to Anheuser-Busch and see what they think about it.
Hi, my name is Brian, and I'll be talking about the process synthesis and process description. For the first round of process synthesis, we eliminated 2 of our 5 initial ideas for distillation units. We eliminated absorption and liquid-liquid extraction. We further researched freeze distillation, gas stripping, and vacuum distillation. We went through and decided what outlet stream ethanol percentage we wanted for each, how they were going to be fed into the system, and what final ethanol percentage we wanted to feed into the system. For our second round of process synthesis, we were able to eliminate gas stripping, and then we further researched freeze distillation and vacuum distillation in their entirety. We changed freeze distillation from having a 60 to 80% ethanol stream to 15% ethanol stream. For process description, this is the current process being operated at Anheuser-Busch, and we are focused on the operating temperatures, pressures, and energy usage for the reboiler and condenser of the main distillation column. Right now, their feed percentage is 4.5% ethanol, and their final output is 86% ethanol. This schematic shows the implementation of the freeze distillation process, where a contherm is operated just before the waste tanks. This allows the ethanol stream to come to ambient temperature once again before being heated by the preheater, further reducing energy usage. The output ethanol percentage for this process is roughly 91% ethanol, which is slightly higher than the current process. This is the schematic showing the implementation of the vacuum distillation process into the current process. It is placed after the degasser, which is after the waste beer is heated by the preheater. The output stream from the vacuum distillation column is fed directly into the main column. For this process, the outlet is roughly 86% ethanol, which is comparable to the current process at Anheuser-Busch right now.
I will be talking about the sustainability of our project. Of these 6 pillars, you can see in the chart our confidence ratings on each of them. To start off, environmental performance, we feel really good about. Our overall goal here was to reduce the amount of waste of each stream of each of our different processes that we are presenting. Next is product stewardship. This will just depend on the product selection from Anheuser-Busch. We have market competitive analysis breakdowns on each of these products. Next is innovation. We've done a really good job of being adaptive to the different challenges that we've had. We've had to eliminate some processes while gaining some processes and opening ourselves to the idea of a combination of 2 or more processes. So we've been really innovative throughout this entire process. Next is social responsibility. This ultimately depends on what final process Anheuser-Busch chooses to select from the ones that we are presenting. Next is value chain management. This in itself has a lot of pillars, including disposal, use by customer, distribution, and management. A lot of these will depend on what process is selected, especially disposal, because while we do know what each system will need to have disposed, we won't be able to give an exact rating and percentage until they select that final process. Next is going to be used by the customer. Again, our customer is Anheuser-Busch, so it just depends on what process they select. Distribution will also depend, and same with management. Lastly is strategic commitment. This is very much based on the company. So it's very important to note, because we are using such a large scale company and working for such a well-known company, this was never really a concern for us. So we feel pretty good.
Due to the scale of the process, there are many safety hazards. The top 6 that we found are shown. Explosions and flammability are related to ethanol concentration, and their solutions include sensors, alarms, and different prevention methods. The health hazards associated with ammonia can be solved by sensors as well as personal protective equipment. Low temperatures, high temperatures, and slippery floors are also common hazards, which can be solved using warnings, sensors, and a lot of personal protective equipment. Here's a snapshot of our process safety risk assessment. The table on the left shows the likelihood on the y-axis and the consequence on the x-axis of different risks for each of the processes. Vacuum distillation is in blue, freeze distillation is in orange, and gas stripping is in green. Risks that lie on the left side of the graph, especially on the lower side of the y-axis, are the most concerning. The key results we obtained from the process safety risk assessment was that gas stripping is an impractical design due to numerous highly likely risks and unsustainable column packing waste. So we did not look into it further. Engineering process controls are used in systems to automate safety so that operators are not put in danger. The image to the left shows the 5 feedback control loops that we designed for our processes. The control scheme pairings are shown on the right. The 5 control variables that we determined to be the most significant for these systems include exiting ethanol concentration, combined feed ethanol concentration, condensate tank level, reflux tank level, and stripping column pressure, so that the process can remain safe.
Hello, everybody. My name is Chris, and today I'm going to be talking about the optimization. So that's kind of our whole project, was to optimize this process, both the existing process and our pre-distillation units for energy consumption, because energy consumption is directly related to the economics. So there's a graph showing the energy that we could potentially be saving with some diminishing returns as we increase the ethanol feed concentration. But also with this energy savings comes lots of economic savings, with about $3,000 per year savings from the freeze distillation. This is purely because they can recycle ammonia in the facility. And with the vacuum distillation, it ends up losing about $3,500 a year. And this is all shown in the bar chart. And then with the return on investment and the payback period, they kind of want like a 15% ROI and a 2-year payback period. But we calculated a 2.4% ROI and a 12.2-year payback period. So with that, gas stripping was kind of discarded with the safety and sustainability concerns. Vacuum distillation ended up not being as profitable as we thought. And then freeze distillation can be a solution to this problem. For future work, we were thinking maybe you could cut down on some of the capital costs by repurposing a contherm, specifically for this product recycle process. And then also just future down the line, maybe in another senior design project, we can work with reducing the plant fuel cost by repurposing the ethanol and not just selling it off to gas companies. Thank you so much for listening.